in to get help, you get 2 points per week. 2 points per day, 4 points max per week. All right, so what else can we do? I like Laney's idea, right? Because if we were able to figure out this hypotenuse, then we get the area of the square for free because that side would be, you know, that times itself will get us the area. So that's cool if we can figure out that hypotenuse. What else do you see?
Mac?
Yo.
It looks like the 27 could be like a fourth of the big box.
Yep, could be. We don't know that for sure, right? Because it's not drawn to scale, but it could be. Another class pointed out that 27 times 4, if it did go in 4 times, would be 108. And 12 also goes into 108. Goes into it 9 times. And 3 does also 36 times. So it could be. So one of the guesses they had was that this was 108. Now, does it have to be? No, obviously, right? We're assuming that they fit inside. But it's a good guess, right? That's fine.
Can we turn the box?
What do you mean, like this? Yep, you can do that.
Do we know
This just hurts me.
that all those sides would be the same?
On the box, this one?
Yeah.
Yes, it is a square. Yep.
Oh,
No, it's cool, it's cool. It's okay. That's the only one we know to be a square. All the rest are rectangles. They could be squares, we don't know, right?
If we're trying to find the area of this triangle, of this
Yep, a square.
square, don't we just try it? Okay, you know, like we drew. Okay, so the 2 triangles, the triangles that we made.
Okay, this big one and this big one, yeah?
Yeah. Couldn't you put that on all sides and repeat that, and then you know the measure of each side, and then you just multiply 2 or find the area.
So if we knew this hypotenuse, then we could multiply it by itself to get the area?
Yeah.
Yes, but how do we know that hypotenuse, right? That's going to be the...
A squared plus b squared.
Yeah, but we don't know these guys, right? These sides. If we did, then we can use it to find the
You
hypotenuse.
can just count.
No, it's not drawn to scale.
Hold on.
Can't use the boxes. I drew it on graph paper to help me draw it. That's all.
Oh wait, never mind.
But good thought, right? Yeah.
I don't know if it's relevant, but I was gonna say, you know, the 90-degree angle right there, and you know that there's 3 triangles. I don't know if it's relevant, but like
3 triangles. What are you talking about?
on the original side, or the given side.
These 3? Yep.
There's 3, and each of their angles, they all add up to 180.
Mm-hmm.
And is that relevant?
So we know that these are all right triangles, right? And we know that because the box has a right angle, right? Each of these boxes has a right angle, which means by linear pair, these must be right angles. So these are all right triangles. Cool.
The other one was.
That's true. All right, 5 more minutes on this one, and then we'll move on. We're not finishing it today. It's okay. That's not the goal. I just don't want to spend all class on it. What else do you see? These numbers? Yeah, they're going to help you figure it out. Without those numbers, you couldn't.
Oh my god, time for your rain will be.
Well, wouldn't
I don't
those,
know.
since they're both right triangles,
Oh, wait, hold
wouldn't all the numbers apply to each side, right?
These, what right triangles? These ones? The small ones?
Small ones, since they're right triangle,
They
they're
should be
similar to
similar.
the big one. So then that way, the 3 and the 27 apply to.
All right, so Schlaffer's saying these 3 triangles are similar. But the problem is, to prove similarity, we need double angle or side, 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 or side, angle, side, right? All I see is angles. So if we can get another set of angles, we can prove these 3 triangles similar. That's true. Yeah.
Don't the big triangle and the little triangle share an angle in the corner?
This big triangle and this little triangle do share an angle.
And the one at the bottom, the one at the bottom too.
So this angle right here is shared between this tiny guy and the huge guy, right? That Laney drew. So they're similar. And then also this angle down at the bottom is shared between this one and this one, so they're similar. So we got small, medium, large, and huge. So small and huge share an angle, so they're similar. And then large and huge also share an angle, so they're similar. That's interesting. So if we knew how this triangle was, we could use similarity to figure out how this triangle is, right? And that would get us the
You
side.
know what the other side should have
Over here?
done? Yeah.
Yep. So it turns out that this triangle right here should be similar to that, right?
Yeah.
I see
Yep.
parallel lines.
Now, hear me out.
I can't really see the lines on the outside. Where your box is. But the red line.
Does this help?
Oh, these guys?
Yeah.
Sorry. right? This
Oh, yeah,
is
those are all right.
all right angles. What else we got? Schlaffer, would you have something to say?
Yeah, well, I just forgot. Oh, I see parallel
Yeah.
lines.
You could, right? Whatever's left over here. So this is right angle plus green will get us that, right? That's what's left over. So doesn't that mean that this is right angle and green? So those two angles are the same, aren't they? This angle right here is 180 minus the right angle minus the green, right? That's what that guy is. This is also 180 minus green and red. You see it?
Yeah.
So they must be the same. And not only that, but what Schlaffer said was true. If we extend these out, these lines are all parallel, and then this one down here.
So you can use cap.
So we can use cap to say that these are all the same. And then we said this is the same as this by LPT, right? Or by angle addition postulate. So that means these must all be green. Again, those aren't vertical. Now, isn't this also a right triangle? So if it's a right triangle, and that's blue, what should this angle be? Green. Nice job, nice job, nice job. Good job, Schlaffer. Good job, Kozovic. Good job, everyone.
I think the hard part is like drawing the shape.
Yeah, drawing it is not easy.
I didn't draw that.
Don't try to be accurate. Yeah, take a picture if you want, but it's a good question. How do we get those numbers to apply to those triangles? Because we get it for the triangles, right? And we can win. But we did prove that this big triangle is similar to all these guys. So if we knew one of them, we could apply it to this triangle through similarity, right? If I know one triangle is related to another, right? That's 3, 4, and I know that this triangle is similar. The relationship is times 2, right? So it can help you get the missing side,
But you don't know what the side is.
right? We could do Pythag if they're right angles, right? Right triangles.
You know one side, 3, 12, and
We're not going to solve it today. We only get a minute left.
Did anybody solve it today?
No, of course not. This is a really hard problem. It's worth doing.
just that. Can we just come up?
What else do you see?
Area. What's area's formula?
Why did I draw these boxes?
Like 3 boxes, it's like bottom. The area from always a triangle.
Hold on, I can't hear Alicia. What are you saying?
Why do you draw the 3 box? All the way like
This?
up, yeah, like up next to the.
That's going to help you figure out how long this is.
That looks like the square
Ma'am.
It's a tough question.
though.
This makes no sense to me.
Well,
So
I was gonna say, like, since
How do you
follow kind of make up one side,
Yeah.
and then they're
the house that I thought that was my alarm.
So, these are not the heights of the boxes. If they were, we could add them all up and figure out how tall this part was, right?
Well, we could do that. Just get like.
But we don't know that they're the heights, right? That's the area.
So we.
Close. Last thing I'm going to add is that this triangle shares this angle with this triangle. So these two are similar, so this must also be green.
That alarm scared me.
I'm tired of looking at triangles.
Yeah, same.
Oh, get used to it.
No.
Mix it up and go to squares.
Today we're going to talk
Can we
about
mix it up
circles and triangles. So,
Oh, we're about circles
Oh, we're gonna do that campfire song
little bit.
inside the circle.
all right, this is period 6. We'll come back to it. All right. Good job today, guys.
How far did we get?
Do we make it
Pretty
farther
far.
than the other class?
Oh, you guys care about that so much. So
Yeah, we do. Here, where'd they get to?
I try not to give people bad news. All right.
We didn't get that far then. We. Yeah.
I'm also
That's
a
the other
liar.
one.
Just watch the other,
Yeah, we know that.
the other live streams and you'll find out.
True. Let me go look it up. I know.
Mr. Mayor, you seem slumped today.
Nope. So, let's take a look at this thing first.
You did some.
Talk about triangle segments, right? Now, that's the color copy. Here's the black and white copy.
So an accent is horrible.
Thank you. So, we've talked about triangle segments before, special segments and triangles, yes.
No.
Yes.
Not black.
Whoa.
Oh, well.
Thomas, it's not like anybody isn't a fiend at some point.
Well,
Whoa.
there you go.
Whoa.
All right, so we've talked about triangle segments before. We just haven't really called them anything. At most, I might have done it in passing. We've actually talked about medians. We did a proof where the medians, where they intersect, will always be like this will be half of whatever that is, type of deal, where the two medians intersect. We did a proof about that. We'll come back to it. We also did this one. If you take the midpoints of all the sides and you connect them together, right? You make the triforce, right? And we call these segments mid-segments. Remember that this will always be twice as big as this guy. You guys remember that? We proved that this will always be twice as big as that. And they'll be parallel, right? We call these mid-segments of the triangle when you're connecting midpoint to midpoint. What we're talking about today are medians, which don't connect mid-segment to mid-segment, or midpoint to midpoint. They connect vertex to midpoint. Why do we call a triangle a triangle?
3 sides.
3 angles, very good. It's not a tri-side, it's a triangle.
Oh, yeah.
So, there are 3 angles in this triangle. The vertex of an angle, remember that's where the angle comes together, right? That's the vertex. So we have 3 vertices, that's the plural of vertex. If we go from a vertex to a midpoint, we call that line a median. So this line right here is a median.
Kind of like the middle.
Kind of. So, midpoint to a vertex, vertex to a midpoint, that creates a median. We good with that? This week's going to feel an awful lot like it would feel like if I was a regular geometry teacher. There's going to be a lot of terms and definitions, and that's going to be basically how you pass the quiz. I don't like doing that because I don't think memorizing stuff that you're never going to use is important, right? Which is why when I teach geometry, I avoid that at all costs and instead try to teach you how to think about things differently, which you'll use all the time, right? Will you use triangles and circles all the time? No. But these challenges will help grow your brain, and that you'll use all the time, right? Memorization doesn't grow your brain. You eventually forget it, right? And it's not really learning, so I think it's a waste of time. But in order for us to talk about this stuff and prove it, I want to have some terminology down. So this week's quiz could be very easy. It could be like a regular geometry quiz. Just be glad we don't do this every week with memorization.
So we have
Awful.
a quiz Friday.
Oh, yes. So, median, midpoint to vertex, angle bisector. They call it angle bisector because it cuts the angle in half. So this line, where it hits the other side, doesn't matter, right?
Don't care. Don't care.
All we know is that those 2 angles are the same.
Bisects, wait, does that mean?
It bisects the angle.
Well, yeah, but that means they're
Whoa.
cut in half, right?
Cut in half, yep. It's not just cut into 2 pieces, it's cut into 2 equal pieces, right? To bisect the angle.
Watch your language.
So, you with me? All right, vertex to midpoint, median. We good? Vertex to who cares, but it cuts the angle into 2 pieces, angle bisector. Okay? Oh, it looks like it cuts it in half. We don't know that. This definitely cuts it in half because that's a midpoint, right? It tells us that. So, vertex to midpoint, angle bisector. We cool?
Where does it tell you the midpoint? Is that what the dot means?
Well, it's the midpoint because it cuts it into 2 equal pieces. These 2 pieces are congruent, right? Good question. Next one, 4 different names. They all mean the same thing more or less, okay? So don't worry about this one down here. So this one, the height of the triangle, you guys have been doing that for a while, doing area of triangles, right? The height of the triangle, this line that forms the height, it can keep going if you want. We call that the altitude. We also call it a perpendicular because it hits it at 90. Is everybody cool with that? Right? Perpendicular means hit at 90. So it goes from the vertex to wherever it hits on the opposite side that makes it 90. Okay? Does it cut it in half? Maybe, but it doesn't say, right? All it does is go from vertex to 90. Are we cool with that? Now, if I flip the triangle, I could also go from vertex to this side at 90. It'd be about there. From this vertex to 90 would be like here, right? Or maybe straight across because that's a 90-degree triangle. I don't know, right? So it depends on which side we call the base, but we can find all the different heights, altitudes, or perpendiculars. The name that you're really going to want to remember is the one that's the hardest to remember. It's orthogonal. We're going to be using that word a lot. Now, when it comes to two-dimensional geometry, orthogonal and perpendicular means the same thing. Right? Two-dimensional geometry, the red pen and the black pen are perpendicular, right? Also orthogonal, same thing. But if we go 3D, orthogonal and perpendicular aren't the same thing. So notice that right now everything is perpendicular to the other line. So red and blue are perpendicular, right? There's a 90-degree angle here. Blue and black are perpendicular, and of course they're perpendicular between black and red. When everything is perpendicular, we call it orthogonal. Now, in 2 dimensions, there's only one way to do it, right? There it is. Perpendicular, same thing as orthogonal. But notice that if I do this,
How would it be?
are black and red perpendicular? No, they are not. What about red and blue?
Oh, cool.
They are perpendicular, right? What about black and blue? Yes. So you see how in 3 dimensions, some things aren't going to be perpendicular. But because this right here is 90 degrees, we can call that orthogonal. All 3 are more or less orthogonal.
How was the black?
The black and the red are not. But the black to the blue is.
Oh.
Right? In 3 dimensions. So in 3 dimensions, there's some, persnickety stuff about orthogonal and perpendicular. For 2 dimensions, they're interchangeable. Just know that. You're going to want to remember orthogonal, though. Okay? It's basically the height of the triangle or the perpendicular. Does it cut it in half on the other side? I don't know. Maybe. It could. Sometimes it might. But all we know is it hits it at 90, okay? So to review, vertex to a midpoint, median, cuts the angle in half, angle bisector. That one makes sense. I hope you guys get that one. The height of the triangle, also known as an orthogonal or an altitude or a perpendicular, hits it at 90. That's all we know. From a vertex to 90. Cool. The weird one, the really weird one, is perpendicular bisector. It looks weird. So it starts off being a bisector. Not of an angle, because otherwise we call it angle bisector. It bisects a side. See how it cuts it into 2 equal pieces? That's a midpoint, right? So it goes from the midpoint up straight from 90 degrees. Does it hit the opposite side at a cool point? No. Does it hit the vertex? No, not necessarily, right? It could. A lot of you guys are going to construct these, and it's going to blow your minds. You're going to be like, what's going on? Why can't I make this? And you're going to think, okay, there's the midpoint. Connect it. And what you're really making is a median. And then you're like, okay, now how do I make that 90? Well, you can't, right?
It just doesn't work.
You have to go from here. Don't start here. It has nothing to do with the vertex. Start here and then make it 90. It's going to be a weird one to make. So if I rotate the triangle, it's easier to see. This looks like the midpoint, right? 90 degrees from there is here. Does that make sense? It doesn't go across to the other vertex. All right, this one. If I cut this in half, there's the midpoint. 90 degrees from there is straight up, okay? That's how we construct perpendicular bisectors. They are both perpendicular, because they're 90 degrees, and they come from a bisector. Not an angle bisector, a segment bisector. We call that from midpoint straight up at 90. So median, vertex to midpoint, angle bisector. Cuts the angle in 2. I swear to God, you better get that one, okay? Orthogonal means perpendicular. And that's all we know about it, right? It's from a vertex to perpendicular. And then perpendicular bisector is from a midpoint perpendicular. Okay? Think you got it? We'll find out. Look at the next piece of paper.
The orthogonal or perpendicular, is that the only 2 names we need to put for it?
I'll accept any of these, but orthogonal is the one you're going to want to remember the most.
Okay.
Remember, these mean the same thing.
Yeah.
Okay?
I just didn't know if we needed to put attitude or height.
Altitude or height? Nope, not
No,
necessarily.
I thought it said attitude.
Nope.
I ain't gonna lie.
Why would a triangle have attitude?
Hey, it could.
Do not drink that.
Exactly.
The spot snaps and it's ready.
I'm with you. All right, so don't read the directions. Words are hard. We don't know this stuff yet. All we're going to do is we're going to mark down which ones look like what. So look at triangle number 1.
Where?
Segments AF and BD and CE. Not funny. What are those examples of? What kind of segments?
Angle bisector.
Angle bisectors, because they cut the angles in half, right? This angle's cut into 2 equal pieces. This angle is cut into 2 equal pieces. And this angle's cut into 2 equal pieces. So we have angle bisectors. Write that down, write that down, write that down.
Why?
That just sounded like Bartos.
Legend. All right. Living legend.
You should put him up on the bottom.
I should. I need a portrait of him. Somebody draw me a picture of Bartos.
We need to get a fat head of Bartos. Fat head.
I like what you're thinking. Yes.
Can I?
That's like a before
Yeah,
coming
I
out
should
of
bring
you.
you in some of my drawings,
Yeah.
bro.
Stop throwing pencils.
And you say you can catch a football.
Fumble.
She can. She's pretty good. All right. Angle bisectors. Cool. Number 2. What kind of line segments are those?
Those?
Perpendicular bisector? No.
They're not perpendicular bisectors because they're not midpoints, right?
They're orthogonal.
They're orthogonals or perpendiculars or heights or altitudes, right?
I got you, Mr. Matt.
I'm going to call them orthogonals.
Just because it's cool to write it.
It is, and it's the word you're going to need to know for another thing that we're going to learn later. Okay.
SAT.
Again, they're not perpendicular bisectors because we don't know that it cuts it in the middle. But D looks like it's the middle. It's not. We don't know that for sure. Could they end up being one and the same?
Is.
Maybe. But we don't know that.
Is this?
Number 3. What do you see?
I see perpendicular. No, I don't. I don't know what I see.
What do you see for number
I see
3?
an angle. No, I see.
It's not an angle bisector.
I see a median.
Perpendicular bisectors because they bisect the side and then they come from that at 90 degrees.
Which ones though? Is it top or left?
All 3 of these segments are perpendicular bisectors.
But they don't all form a 90.
They do with their, so they go from the midpoint. See how that's a midpoint? Point D is? Right, it's cut into 2 equal pieces. From the midpoint at 90 degrees. From the midpoint at 90 degrees. From the midpoint at 90 degrees. Has nothing to do with the vertex, okay? If they go through the vertex, great, right? This one's pretty close to going through the vertex. If we change the triangle a bit, it might have gone through it. That's just a coincidence. So perpendicular bisectors. They cut the sides in half and go from there at 90. All right. Number 4, don't do process of elimination, but you can.
Median.
They must be medians because these are all midpoints, right? Midpoint to vertex, right?
Wait, what was number 1?
What is number 1?
Angle bisector.
Angle bisectors because it cuts the angles in half.
Orthogonal.
We're done.
Ow.
See how it cuts this angle into 2 equal pieces?
Yeah.
And this angle gets cut into 2 equal pieces? And this angle gets cut into 2 equal pieces? Angle bisectors. Now, that's just the beginning. Now we need to talk about their centers, right? So what do you notice about all these triangles that I drew? Well, first of all, they're all the same triangle. I just drew the lines differently.
The middle dot's different every time.
The middle dot, G,
Yeah.
okay? This spot right here is in a different location depending on which segments we're talking about, right?
That's right. This is true.
Now, I don't think you're realizing how amazing this is. So I'm going to demonstrate. You ready? Here we go. I'm drawing lines, and lines go on forever, right?
Yeah.
Okay.
I thought it
So here's what I'm going to do. I'm going to close my eyes. I'm going to draw 2 lines. All right?
Yeah.
Will these lines intersect?
Yes.
Yes, they will. Now, should we be surprised that I drew 2 random lines and they intersect? No, because in order for them not to intersect, what must they be?
Parallel.
Parallel. And drawing 2 parallel lines randomly would be pretty freaking amazing, right?
Do it.
So we say that these lines do intersect, and we shouldn't be surprised by this. 2 lines intersecting happens all the time on accident, right? Unless they're parallel, they're going to intersect. We call this being concurrent. So if 2 lines are concurrent, it means they intersect at a point, right? Now, for 2 lines to do that, that's not very impressive, right? Randomly, almost every 2 lines I'm going to draw are going to intersect at some point, right? Unless I draw them perfectly parallel, which just isn't going to happen, right? It's almost impossible. Now, what about 3 lines? Because look, all 3 of these always seem to intersect at a point. Should we be surprised by this? Well, for 2 lines, it's like, well, duh. Of course they're going to intersect at 2, right? Unless I draw it parallel, they're going to intersect. But what about 3 lines? All right, 3 lines randomly. Here we go. Ready?
They do full sends only.
Cool. Well, these 2 definitely are concurrent, right? Now, we shouldn't be surprised because these 2 right here,
Vertical.
it's the same as just looking at 2 at a time, right? Of course they intersect, right? These 2 slightly angle in, they would eventually. They're not perfectly parallel, right? So they would eventually intersect. And these 2 definitely intersect. Again, taking 2 at a time, of course. The odds are they're going to. That's not impressive. Will all 3 of these intersect at the same point?
No.
No. For that to happen, I need something like this. Right?
That's full.
Yeah. Now, that would be pretty rare, right? So concurrency for all 3, again, for 2 at a time, no big deal. We already proved that. But for concurrency for all 3 is very rare. So when we see something like this, where all 3 lines intersect at a point, that's really rare. And not only is it all 3 lines, but all 3 lines, no matter whether we're talking about angle bisectors, all the orthogonals, all the perpendicular bisectors, or all the medians of that same triangle, will all be concurrent. Now, notice I drew an acute triangle. How do things change if we change the triangle? Will they still be concurrent? Let's play around with this. We're going to prove all this stuff, not this week. This week we're focusing on, do you know the names? Can you speak the lingo? Okay? Do you know the properties? We're going to prove all this next week, although we've already proven some of this stuff. Okay?
Nice.
I'm going to show you a program called GeoGebra.
you making fun of me because my pants are see-through?
All I heard was depression.
You're making fun of me because I'm fat?
So check it out. Flopper, I need you to focus in between things for once. Right?
It's hard.
I know this.
It's one.
All right, here we go.
I know.
So we named this in fourth hour.
One, Jacob.
What we created
Cam.
was a bunch of angle bisectors. So here's our triangle.
Khalil and
If you can't handle it, I will delete it. I swear to God. 6 hour, you need to grow up just a little bit.
Why?
So, because I want to have fun, because math should be fun and school should be fun. But you guys can't handle it. So zip it. So, I can move the triangle around. And notice that the angle bisectors all intersect at A. Right? And A is always inside the triangle. Even when it's a right triangle, right? I'll make a right triangle. It's always on the inside. Even when I make it obtuse, it's always on the inside. So for the angle bisectors, they're always concurrent no matter what. And A, the center that they make, is always inside the triangle. So let's go back to what we were looking at. Number 1. Point G has a special name. That spot right there is called the in center. In center. Center with an IN in front of it. In center. But we didn't. So that spot right there is called the in center. It's the intersection of the angle bisectors. And when the triangle is acute, let's draw a little acute triangle, we found out that it was inside, right? And when the triangle is a right angle, it still stayed inside, right? And when the triangle was obtuse, I always struggle at drawing obtuse triangles. There we go. Right? Bigger than 90. We also found that it was inside. So this center, the in center, is always inside the triangle. That's partly why they call it the in center, because it's always inside.
Is that true for all?
Think about drawing a 90-degree angle and then make it bigger. That's what I always do to make my obtuse.
Is
Yeah.
this true for all?
Legit curved the top.
Just for angle bisectors. But we're going to investigate the rest. So the in center is pretty cool. Turns out that the in center is same distance from every side of the triangle. So from here to here is the same distance as here to here, as here is to here. Those are all equidistant. So it's equidistant to every side of the triangle. Now, when we measure things, like from the top of my head to the ceiling, we measure straight up so that it hits the ceiling in a 90-degree angle, right? We don't measure it like this, right? Obviously, I'd be much shorter compared to the ceiling if I measured like this. So we always measure to something at 90 degrees. So from here to here, we measured at 90. From here to here, I measured at 90. From here to here, I measured at 90. Because that's how we measure towards something, right?
Yeah.
And these will all be the same. Now, if those are all the same distance, what would happen if I connected these?
You make a circle.
Be a circle. These are all radii, aren't they?
Yeah.
The distance from the center to the outside of the circle is the same. So if I connected all these, I'd have a circle. And this circle would perfectly fit inside the triangle.
Can you make a
We call this an inscribed circle because it's inside the triangle. Scribe meaning right, in meaning inside. So I'll make the circle as best I can. I'm not very good at it. So if I connected these, right?
Have you tried making a circle with your arm? That's perfect.
Now notice, a lot of people get confused by this. They think that this right here is a radius. No, it's a little bit longer than the circle. It's hard to see, but it is. This one, again, a little bit longer than the circle. This right here, can you see how that's definitely longer than the circle? Right? Will those sometimes be the radius? Sometimes, but very rare, right? It's always to 90 degrees. And you have to draw those in yourself. So G is equidistant to the sides of the triangle. So equidistant,
Is this what our test is going to look like?
yes,
Oh, dear Lord
We have to
Jesus.
draw the circle.
yes.
Are you serious?
How do you guys spell
Equidistant, sorry. Oh, that's why I goofed it up. There we go. Equidistant to the sides of the triangle. My pen's kind of dying out on me, guys. Equidistant. Equidistant, right? So equidistant to the side of the triangle, which means, since it's equidistant to the side of the triangle, that means it forms a circle that perfectly fits inside the triangle, right? So we call that circle an inscribed circle. So the in center is the center of an inscribed circle. that perfectly fits inside the triangle. In fact, it's the biggest circle you can fit inside the triangle. So if you had a triangle box and you wanted to fit a ball inside it, the biggest ball you could fit would be that size ball.
Did manufacturers use this?
No way.
Yep. It's the biggest thing. It's the biggest one you can fit. So if you had like if you're trying to make a necklace and you had a triangle, you want to drill a perfect hole in it that just barely touched the outside, so it still stayed a triangle but didn't break it, right? That would be the center of the hole that you wanted to drill, and the distance that you want to drill would be that radius, and it would just barely touch the outside. So how do we find that center? Well, we find all the angle bisectors, which isn't hard, right? Cut the angles in half, and you see where they intersect, and that'll be the center of a circle that perfectly fits inside the triangle. We call that center the in-center. It's always inside the triangle. Well, duh, right? The circle's always going to be inside the triangle, so of course the center's always inside, right? It's equidistant to the sides of the triangle, and it makes an inscribed circle. Remember, scribe means to write, in means inside. This is one of the hardest ones to remember, okay? It's got the most information. Let me show you what this looks like on GeoGebra. So check it out. Here's our triangle. Now, to measure the distance, so I know how to make my circle, I need to make a perpendicular line. So I'm going to go from A to here, and that hits it at 90. So let me stretch this out so you can see this a little bit better. Right? From here to here is 90 degrees. Do we see that?
Yeah.
Okay, I did that to measure from here to here. That's the radius of my circle. Trust me on that. So now I'm going to make my circle, centered A, and it goes to here. And notice how it fits perfectly inside.
But aren't they touching sides though?
Yeah.
It perfectly touches the side.
So then if you're trying to put a ball in there and try to cut it.
Well, when I put a ball on a table, doesn't it touch the table?
Yeah.
At one exact point, right?
That
So
means
it's
it'll
sitting
fit
on
in
it.
there snug.
If
It
you
won't fit
want to
down.
cut it, you would cut into the triangle and it wouldn't like.
Oh, if you were going to cut it, yeah, you'd have to pull back just a little bit, or have really precise machinery. Yeah. Infinitely small distance between where it hits and where the line is. Yeah. There's a conundrum. So that's the in-center. And no matter where we move the triangle, of course the center of the circle is inside because the circle's inside, right? Obtuse, right angle, acute.
You came up with the name Khalil.
Nelly.
It was only just
Like not the rapper, like the one from St. Louis, but like Nelly's cute.
I was thinking
You
about
love her.
her.
Almost 3 for 3.
Hey, here you go, Mr. Mac.
We'll talk about the rest of these tomorrow.
She was pregnant, but it was so interesting. What's so funny back here?
We good to dip? No. Make sure you know these guys for tomorrow. Bathroom people, make sure you use the bathroom starting in passing period. If it goes over, that's fine. Do not show up when the bell rings and ask to use the bathroom. I will say no, because I'm mean. Mean. Only because I'm mean. Not because I'm going to be consistent with that. The next day I won't do that, but I just want to be mean tomorrow.
Can I have a pass for my room? Can I also
Yeah.
Back here after school and take my
Literally, back there does not work for you.
I don't care.
No, I do care. Back there does not work. You can't sit back there anymore. It's not working for you. Go away.
Tell me my sloppy Where's Mormon underwear today?
Nice.
Matt, why can't you sit back here with me?
It's not working for her.
No. I was genuinely productive today. I came up with valid theories and she shouted them out.
No, literally for real, I'm not gonna lie.
Dead
Okay,
ass.
I wasn't supposed to.
awesome. Then if it works, it works.
I worked better.
But it better work, because your mom's emailing me and asking me how I can help you, and one of the ways I said I would help you is by putting you in front of class, and now you're sitting back there. So it better work, and if it doesn't, we're both in trouble. Carpenter.
She's not that distracting. She's helpful.
2, I don't care whether it is or isn't, as long as the results speak for themselves. During homeroom. That's an R. Boop. For you. You need a pass?
Yep. Don't look at me like that.
We're gonna.
Also, we're going to stop letting 6th hour out early, because you guys work the least hard out of all my classes. I let you guys out early all the time. But you're working the least amount of hard.